So hello, as always a short review from last time. So we started with model selection and the estimation of the generalization cost. First of all, we are considering different loss functions like the squared error, quadratic loss, the misclassification cost, so the number of misclassifications, the absolute deviation, perceptron, we went through that before, Babnik's optimal hyperplane, and cross entropy. So just a few examples. And what we are interested in is to have a model for which the cost when averaged over all possible data, so this is simply what this means. We assume a fixed but unknown data distribution, and if we integrate over that and evaluate the cost, then this is the quantity we are interested in. And here the distribution of x enters, so the input data, and also the distribution of y or y given x. We can consider the average test set error, and this is a good estimate of the performance of a model on generalization on test data, or we can look at the average training data, and we write it like this. So W hat is optimized based on the training data, and we evaluate the cost also on the training data. And then the general result is that so if this is the cost of the training data of the model trained on the training data, evaluated on the training data, this is the model also evaluated or trained on the training data but evaluated on the test data. Then in the expectation over all possible training data sets, this quantity is larger or equals 0. So in other words, the training error underestimates the true generalization error. So we can look at a frequentist view on this. So we have input data which is generated from some distribution x, and here we are assuming a function plus noise, so it's typically we assume Gaussian noise. So and then in the frequentist analysis, we assume that at least conceptually we have many training data sets available of the same size. In practice, of course, we have only one. So we have one training data set. We once estimate the parameters in the model based on the training data set, and then we get one point over here. So this is the size of the generalization error or the training error. So this is the best model can ever do. So it because the epsilon or the noise cannot be predicted. So this is a yardstick, the residual noise. And if you look at the training error on average will be smaller than this quantity because of the effect of overfitting. So we also will a little bit or more or less reduce the error by overfitting. And in some cases, this is, so the residual is a sigma square, it's residual minus what we will call variance, and the test error is residual sigma square plus the variance. So so from the training error it might look like a good model, but when we add 2 times the variance, the generalization performance might be worse. So in general, it means that in training we don't get the optimal model, we get some model, and based on the training data it looks very optimistic, but if we would look at the test error, we see that that's really larger, and that's what we are essentially discussing in this lecture. And but in practice, we are typically not so much concerned about the theoretical underpinning, but we want to have something in our hands to decide which model is the best from the models available. So we might train whatever neural network, linear system, fixed basis function system, kernel system. And if we have a lot of data available, and this is more the case nowadays than ever before, and this is in fact what people are also doing, you divide your available data into training data and test data, and you also publish your data with this particular split. And then you're training your model however you want on the training data, and you then, after you're done with your training, you can test it on the test data. And ideally this should be well separated, and you should not optimize your model at all on the test data. You should even not do some sort of first selection on the test data. All this makes your model look better than it might really be. So this is the simplest case. Just divide your data, training on the training data, and then test it on the test data. And the test data evaluation is sort of an unbiased estimator of your generalization performance. If you don't have so much data, you can do cross-validation, which is what is really recommended, but people often don't do anymore because there's too much data and the tuition got lost a little bit. So it's a similar idea. So you leave out, so the rest one is the red one here. The red set of data is left out for testing. The blue one is used for training. And then you change the set which you use for testing at each experiment. And you're always training on the blue and you're testing on the red. So each data point is only exactly one time in the test set, otherwise it's in the training set. So the good thing is, for each time you have a lot of data available for training. And also you can not just look at the average performance of your test data set, you can also look at the standard deviation and then decide if one model is actually better than the other model, based on the uncertainty of this estimation. So this is how you calculate the variance of a particular model. So it's essentially an empirical difference, and you can divide by k and times k minus 1, because you're not interested in the variance of the different models, but in the uncertainty in your estimate. So that's why you can divide it twice. And then you say that MI is really significantly better than MJ if performance of the mean performance of MI plus the variance is smaller than the mean performance of MJ minus the variance of MJ. So in other words, that the standard deviations do not overlap. So that's when everybody sort of accepts your conclusion. If they overlap, then you can do something like the pair test, where in each experiment you look at the difference between the two models and analyze if this is significantly larger or smaller than 0, to make this prediction or decision if one model looks better than the other. So here the difference is always positive, despite a great noise in the individual performance of the individual models. And there's also something called Wilkinson's test, signed rank test, which is an alternative to this paired t-test I was discussing here. But you also have often hyperparameters you need to optimize, particular the weight on the regularization parameter lambda, or if you want to do stop training, when to stop. So ideally you take your training data here on the left side and again divide it up into two sets, and one is the actual training data and the other one is sort of a left out data set in training on which you tune your hyperparameters. And if you're done tuning, you can use all the data for training, because you can do whatever you want with your training data as long as you don't touch the test data. But you often have an inner loop where you also try to optimize the hyperparameters, because you should definitely not optimize the hyperparameters on the test data. Don't take the performance which is simply the best on the test data, because that would also easily favor your model unfairly, and in particular if you have more than one hyperparameter to tune. And this is a typical learning curve or training curve and test curve we are observing. So the training performance, so this is some prediction error or some cost, goes down and down and down, and the longer you train, the better it looks. But that's why you have to look at the test sample, and then you see a minimum, and it goes up again. So this is the model maybe you want to choose, where you have the best test data performance, and this is some measure of complexity, and it can be training time if you do stop training, or can be related to the regularization parameter. So here you have low regularization, here you have high regularization. Okay, so here was one comment on the search of the best hyperparameters. So people have long thought about how to do that, in particular if you have more than one hyperparameter, and the story is probably not finished, and there might be better solutions available, but it's not bad to just do random selection of hyperparameters and then decide on the best one on the random selection, because you want to explore the whole space, and if you do something smart, you might not explore a space and parameter space where you should explore. For example, if only one, let's say you have 10 hyperparameters, but only one is really important and the other ones are relatively unimportant, then it would be important that you explore the one which is relevant. And the easiest way to do that is to select random hyperparameters. Then you're definitely exploring the space of the one you're interested in. But it's still an open research question, and a lot of work is being done in this direction. Okay, that was it, and the next lecture will be more on different theories on learning theory.